The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So I'm back. Welcome back also to AO3. Today, what we are going to do is something really interesting. So it's to understand how we use symmetry to help us with prediction of physical situations. So first I will go through two concrete examples of symmetry and see what we can learn from there. And also today we are going to go to infinite number of coupled oscillators. Okay, I think we are done with finite numbers. Okay. All right. So what we have learned last time when Bolek was giving the lecture, I hope we have learned a driving force can excite a specific normal mode, right? So if you drive the system at the frequency the system like, then the system will respond and oscillate at the driving frequency with large amplitude, okay? And also, we have learned that the full solution of a coupled oscillator is actually pretty similar to the situation we got from single oscillators, right? So you have particular solution and the homogeneous solution. And the full solution will be a superposition of the two components. And all the unknown coefficients are in the homogeneous part of the solution, okay? And today, I hope I can help you and convince you that symmetry actually can help us to solve the normal modes without knowing the detail of N-1 matrix, actually. So that is actually something really cool, and I would like to talk about that in this lecture today. So this is actually what we have been doing so far, right? So we write everything in terms of matrix. So we start from the equation of motion, and x double dot equal to minus kx. And then we write everything in a complex notation, exponential I omega t plus phi times a. A is actually a vector, right? So it's actually a1, a2, a3 is actually the amplitude of the oscillation of the first, second, and third, and et cetera, component of the system, right? Then we actually found that in the end of the day, we are actually solving this problem like an eigenvalue problem, right? So basically, we have n-1k matrix describe how each component in the system interact with each other, okay? Then what is actually the angular frequency of the normal modes is actually coming from this eigenvalue problem, n-1k a equal to omega squared a. Then you just go ahead and solve the eigenvalue problem. Then you will be able to figure out what are the normal mode frequencies, and therefore what are the the ratio of the amplitude in the normal mode, which is actually the a vector, okay, the eigenvector. Okay, so that's actually what we have been doing. Okay, and today what I'm going to do is to introduce you a very important concept in physics, not only in physics, but also in mathematics, and also art, right? So you see symmetry in the art, for example. So you can see here, there are several graphs here, and you can see that there are apparent symmetry, you have rotational symmetry, there are refraction symmetry, and you can see that when we build the a particle detector, for example, lower right plot is a CNS detector, compact muon solenoid in the Large Hadron Collider. We also try to build this detector symmetric, right? Because otherwise, if I get a very complicated shape of detector, then the analysis of the data will be really complicated, right? So therefore, everybody likes symmetry, and everybody don't like really chaos, right? Okay, so that's really nice. The question is, how do we speak the language not like the nature speak? How do we actually describe symmetry? That's actually the question I'm asking. And I'm going to show you that, okay, we can actually use mathematics to describe a symmetry. So before we go to infinite number oscillator, let me give you a concrete example of symmetry and then see if we can understand how to use the math to describe symmetry. Okay? So there's a two-component system, two pendulums, which we worked together in the last few lectures, that they are coupled to each other. And there's a apparent symmetry of this system. Can somebody tell me what is the symmetry you can see from this system? Somebody? Anybody?
Reflection.
Refraction symmetry, right? So if you refract this system, as I show you in the slide, you can see that if you refract this picture, it looks identical, right? So that is actually really very, very good news. That means if I do this refraction, x1 go to minus x2, you have a minus sign because you can see that after refraction, the amplitude changes sign, right? x2 go to minus x1, the system looks identical, and the physics should not change. Okay? So that's actually what we can learn from there. So that means if I do this refraction, then I can have actually define x tilde t. This is equal to minus x2 minus x1, okay, to be compared with x, okay? And this is also going to be the solution of the equation of motion if the original x is already a solution, okay? So that's the power of the refraction symmetry, okay? If x is a solution, then I do this refraction, and I can figure out that x tilde is also a solution, okay? So how do I actually describe this symmetry in the form of mathematics? What we actually do is to define a S matrix, symmetry matrix. And in this case, when we talk about refraction symmetry, it's actually defined as 0, minus 1, minus 1, 0. This is actually a 2 by 2 matrix. And if I do this operation, S operate on this X matrix, then that is actually going to give you the X tilde. Okay, so that's actually the role of the symmetry matrix. Okay? Any questions? Okay, so now we have defined a symmetry matrix, and then you can ask, why do we actually care, and why do we actually introduce symmetry matrix, right? Because I can always write down the X tilde in that way. That is because I think by the end of this lecture, you'll find that if S matrix describe the symmetry of the system, okay? That will mean S matrix will commute with n-1k matrix, which you don't know commute yet, but I will introduce you. That means n-1k matrix and S can actually swap freely, okay? If that happens, then S matrix will share the same sets of eigenvectors as the n-1k matrix. What does that mean? That means, okay, before we're doing this solution, right, we are solving n-1k matrix eigenvalue problem, right? And then we get the eigenvector, which is the amplitude ratio of normal modes. And that means you have an alternative way to get the normal mode. You can solve the eigenvalue problem of S matrix. Then you can get the same set of amplitude ratios as n-1k matrix eigenvalue problem. Okay? And usually, the eigenvalue problem of S matrix is far much easier than n-1k matrix. Okay, so that's actually why we are doing this. Okay, so now I would like to convince you that S matrix and the n-1k matrix will share eigenvectors. Okay, so let's go ahead and prove this or demonstrate this idea. Okay, so the original equation of motion looks like this: x double dot, okay, equal to n-1k x. Right? So that is actually the original equation of motion. Okay, and if this system satisfies the refraction symmetry, that means x tilde is also a solution, right? Therefore, what does that mean? That means x tilde double dot will be also equal to n-1k x tilde, right? Because it's also a solution to the equation of motion, right? That's pretty natural. Okay. Now, I can actually use this expression. X tilde is equal to S times X, right? All of those things are matrix, okay? Just to be careful, okay? That means I can write this like this: Sx double dot equal to n-1k Sx. Okay? There's no matrix. And also I'm just replacing x tilde by Sx. Okay? And also, I call this actually 1. I call this actually 2. Okay? I can multiply x from the left-hand side of 1. Okay? And see what will happen. So if I do that, then what I am going to get is Sx double dot. Okay? That will be equal to Sn-1k x. Okay? If you compare this equation and the equation number 3, these two equations, you will see that left-hand side is the same, right? Right-hand side, something interesting is happening. n-1ks must be equal to Sn-1k, right? What does that mean? This means that they are the same. n-1k s is actually equal to Sn-1k. So, if I say this system satisfies a symmetry described by S matrix, that means x tilde, which is actually the transformed amplitude, will be also a solution to the equation of motion. And therefore, an inevitable consequence is that n-1ks will be equal to Sn-1k. Usually, when you study physics, we write this in terms of commutator. Okay, so we call this actually, these two things actually commute. Okay, so commutator is actually defined as A bracket of A and B. This is actually defined as AB minus BA. Okay, if A and B commute, okay, it's a new word probably for most of you. If they commute, that means A, B in the bracket is equal to 0. Okay? So this expression, I can actually write it down like this. Commutator of Sn-1k, that is equal to 0. And you will see this really a lot when you study quantum physics. Okay? So I hope this actually gives you some flavor about commutator. Okay? So now, that's actually pretty nice. This means that they commute, okay? If I take x of t, this is equal to a1 cosine omega 1t, okay? So this means that A is actually X is actually a solution which is a normal mode solution, right? And A is actually amplitude, the vector, the amplitude vector of the first normal mode, and omega 1 is actually the first normal mode frequency. Okay, if this is the case, okay, then I will have x tilde of t will be also proportional to a1 cosine omega 1t, right? Because if I actually exchange x1 and x2, their oscillation frequency is not going to change, right? Therefore, since this system is in the same normal mode with angular frequency omega 1, therefore, the amplitude ratio of the first and second oscillator will stay constant, right? Because you are in one of the normal mode, right? Therefore, I can conclude that x tilde is going to be proportional to this expression because they are in the same normal mode, oscillating at the same frequency. Okay, is that too fast? Everybody is following? Okay, so that's nice. So this means that Sx of t, okay, will be equal to Sa1 cosine omega 1t, okay? So this is actually coming from here, right? I'm replacing x tilde by Sx based on this definition, okay? Then again, I write x explicitly, which is actually a cosine omega 1t, okay? Then you get this expression. And from this above, the expression above, you see that you will conclude that this is proportional to a1 cosine omega 1t. That's very nice. That means Sa cosine omega 1t is proportional to a1 cosine omega t. And you can actually cancel this. Then you see that Sa1 is proportional to a1. Or I can write it as Sa1 is equal to beta A1. What does that mean? This means that A1, okay, originally, where's A1 coming from? A1 is the amplitudes of all the components in the first normal mode, right? That's coming from the eigenvalue problem, which we actually does in this slide. Eigenvalue problem n-1 Ka equals to omega squared A will give you the solution of normal mode and their eigenvectors, which is amplitude ratios of all the components in the system, right? So that means A1 is not only n-1 K matrix eigenvectors, it's also eigenvector of S matrix. Okay? So that is actually a very good news. And I can also do the same thing for A2 to prove that it also works for A2. The deviation is identical, so I am not going to do that again. So that means actually starting from here, okay, if x and x tilde are both solution to the equation of motion, okay, I will conclude that S matrix and the n-1 K matrix, they commute, okay? How to tell if a system satisfies a specific symmetry defined by my symmetry matrix is by this way. You can check if n minus 1k and the s commute. If they commute, that means this system actually satisfies this symmetry. And also, the consequence is that from there, you will conclude that if you have a set of eigenvectors from n minus 1k matrix eigenvalue problem, and that is going to be also the eigenvector of S. Okay? Any questions? Okay. So m minus 1k eigenvectors are also S eigenvectors. Okay, that's actually what we have learned from this small exercise. Now, you can say, wait. This is actually not what we need, right? We would like to argue that S matrix, I can solve S matrix eigenvalue problem, then I can learn about the solution of n minus 1k matrix, right? This logic is actually in the opposite direction, right? You say that, okay, you solve things already, then actually it's also S matrix eigenvalue problem. So now what I'm going to do is to reverse the logic and see if it works, okay? Again, to see what will happen, okay? So now I would like to prove that if I solve S matrix eigenvalue problem, I have also solved the eigenvectors for n minus 1k matrix. Run the logic in the opposite direction, okay? So if we are given two things, one, SA is equal to beta A. Number two, S matrix and the n minus 1k matrix commute, okay? If those are the given conditions, okay, then I can actually conclude that S n minus 1k A, okay, I can actually construct this expression. I write down S n minus 1k A, okay, because they commute, right? I can actually swap n minus 1k and S safely without actually introducing any more terms. And this will be equal to n minus 1k SA, okay? And the SA from the first expression, SA is equal to beta A, right? Beta is a number, okay? Therefore, this expression will become beta n minus 1k A. So beta can penetrate through matrix because beta is just a number. It's an eigenvalue. It's an eigenvalue of S matrix, okay? So what does this mean? Okay, so what does it mean? So this means that if you look at this part and that part, you look at the beginning and the end of the expression, you immediately conclude that n minus 1k A, okay, this expression is also an eigenvector of S matrix, right? So you have an S matrix acting on n minus 1k A, and that will give you something proportional to n minus 1k A. You see? It's a magic, right? It's actually not magic, but it's actually just, really logical extension, right? Okay? Very cool. So that means this is also an eigenvector of S, right? And also, another thing which is interesting is that they share the same eigenvalue, beta, right? They have the same eigenvalue, right? Okay. So if eigenvalues of S, so you can get several eigenvalues, right? In this case, 2 by 2 matrix, you will get how many? 2, right? 2 eigenvalues. If those 2 eigenvalues are different, then I can conclude that n minus 1k A, okay, must be proportional to A, right? Because this is actually the same eigenvalue problem and the same eigenvalue beta. Since all the eigenvalues from the solution of eigenvalue problem of SA equal to beta A, those eigenvalues are all different. Therefore, I can argue that n-1 Ka is proportional to A. Okay? Therefore, n-1 Ka is equal to omega square A. Omega square is actually some constant. Okay? This is actually amazing because that means given the two conditions, the first one, I can figure out the eigenvalue and eigenvectors of S matrix. Second, if S matrix and the n-1 K matrix interaction matrix, they commute, then I can actually already figure out what are the eigenvectors of n-1 K matrix. Okay? And another thing which we learned from here is that, wow, that's good, because the eigenvectors are already solved. Therefore, I just have to calculate this. It's just a normal operation. It's not the eigenvalue problem anymore. I just multiply n-1 K times A. Then I can actually get the value of omega squared. You see, that's actually much easier than solving the eigenvalue problem of n-1 K matrix. Okay? That's actually very good news. Finally, I think the most important consequence is that, sorry for this. The most important consequence is that once we solve this system, which satisfies the symmetry described by this S matrix, we have solved all the possible systems which satisfy the same symmetry. For example, in this case, I solve a coupled pendulum problem. Okay, they look symmetric, right? And I can, of course, I can draw another one which is like this. It's small circular, and there are two walls, which is actually there are three springs connected to the wall. This problem is already also solved, right? Because it also satisfies the same symmetry. And of course, I can add more, like like this, go crazy, add a bit more. This is also solved, right? Because this is also symmetric, right? I can add more, okay, right? Like this, right? It's also symmetric, right? And this, the eigenvector of this n-1 K matrix eigenvalue problem will be identical to what we have already solved here, okay? So that is actually really amazing. If you speak the right language and cut into the problem in the right angle, you actually found that actually you can solve multiple problems at one time. Okay? Any questions? Okay. So that is actually very nice. And this is actually a very important preparation to the next step, actually. So now we have understood coupled oscillator, and we have learned a little bit about symmetry, right? Therefore, I would like to go to infinite number of coupled oscillator. Okay, so that is actually the next step, which we are going to move on in L3. So this is actually one example infinite system. Okay, I cannot write the whole universe, right? Because it's infinite, so I couldn't include everything in the slide. But this is actually an example system. Okay, looks hopeless, right? In general, we don't know how to solve infinite system, because if you have infinite number of things, they are connected to each other in random ways, then the problem becomes really, really complicated. Okay? In general, I don't know how to solve this problem. Okay? And if you are a double imager, the first thing maybe you would like to do is, now I have this picture, and I can put everything in my computer and see how things evolve as a function of time, right? Of course, we can rely on the computers and see what we can learn from it. And if you are a major of mathematics, you say, no, this is not the problem I'm going to work on. OK, I don't care. But as a physicist, what we are going to do is that, if we look at this infinite system, OK, that's kind of interesting, right? It's a lot of things, a lot of small balls connected to big balls, right? Super big one, and plotting things in log scale. So those balls are really, really large compared to all the other balls connected to this system. Therefore, as a physicist, I'm going to ignore all the other balls. Oh, if I do that, then it becomes, there's some kind of symmetry you can actually see from here, right? What is actually the symmetry you see? There are three balls, they are connected to each other, they are equally spaced. We have a translation symmetry, you see? So you can see that actually that's actually how we actually think about a problem. Of course, different fields have different kind of thinking and different kind of problem they would like to focus on. But as a physicist, I would like to know how this system will work, and that is actually what I'm going to do. OK? So that's very nice. We are going to discuss infinite system. So what is actually the infinite system I'm going to talk about? It's actually an infinite system with space translation symmetry. So to save some time, I have already written down the metrics involving this system here. What I'm interested is a mass spring system, okay? Infinite number of mass and spring, and they actually satisfy space translation symmetry, okay? They are connected to each other by springs with natural length A and spring constant K, okay? And there are infinite number of them actually line up from the left-hand side of the edge of the universe to the right-hand side edge of the universe, okay? I prepared this system, okay? It took me a long time. Okay. All right. But it's very difficult to describe this kind of system, right? So the first thing we have learned from AO3 is that in order to describe this system, I need to define a coordinate system, right? And also have everything properly labeled. So I introduce a label, j minus 1, j plus 1, j plus 2, just to name each little mass I'm talking about. Okay, no other purpose. Then, once I have the label, I can actually write everything, express the displacement of those little mass as xj minus 1, xj plus 1, xj plus 2. That's just the displacement from the equilibrium position of the mass. Okay? And this system will have an equation of motion looks like this. So if now I focus on the little mass, j, okay, then I can actually write down the equation of motion. There are two springs. There are two springs connected to this mass, right? Therefore, you are going to have two spring force, right? Since this is actually idealized the springs with spring constant capital K, therefore I can write down immediately the equation of motion is actually equal to nx double dot j is equal to minus k xj minus xj minus 1 minus, this is actually the right-hand side spring force, minus k xj minus xj plus 1. We have done this exercise before, right, with a simpler problem. Okay? As usual, I can collect all the terms associated with xj minus 1, xj, and the xj plus 1 together, then I get this expression, which actually looks nice. Okay? And I assume that this system is actually undergoing some kind of oscillation. Okay? Therefore, I assume that this is a solution. Xj will be equal to Aj is the amplitude of j's mass. Okay? Cosine omega t plus phi. Omega is actually the oscillation frequency, and phi is actually the phase. And I don't know what is actually omega and the Aj yet. Okay, we would like to figure that out. And as usual, okay, you can actually write down the M matrix. Okay, M matrix is actually really simple. In the diagonal terms are all M, and the off-diagonal terms are all 0, right? And you don't really need to copy them because all of them are actually in the lecture note. M minus 1K matrix, I have already arranged my terms here. Therefore, it looks like this. You have a strange structure. You have 3 terms, kind of in the diagonal terms. And this is actually shifting as a function of number of rows, and all the other part of the matrix are actually 0. Okay, it's an infinite times infinite dimension matrix. Finally, I would like to also write my A matrix. It's the vector of amplitudes, right? So you have many, many numbers, Aj, Aj plus 1, Aj plus 2. Okay? Et cetera, et cetera. Okay? Now, very easy, right? The question is actually can be solved, right? You just have to solve the n minus 1k matrix, right? That's easy, right? It's an infinite number times infinite number matrix, right? Super easy. No, actually not, right? So we are in trouble. I don't know how to solve this problem, okay? What can we do? Anybody have any suggestion to me? Yeah, math department is coming in to help, yes. But actually before asking that, we learned some concept which we just learned, right? There's what kind of property of this system? Symmetry, right? We have symmetry, okay? So this n minus 1k matrix looks horrible, right? But if I write down the symmetry matrix, actually it looks slightly better, okay? So what is actually the symmetry matrix, okay? So one observation we can make from this system is that if I shift this system A to the left, okay? I shift these two mass to the left-hand side. I shift all the mass. I have to hire many, many students to move all the mass from the left-hand side of the universe to right-hand side of the universe, okay? And after they have done that, the system looks the same, right? That's very good, okay? After all the hard work, right? So what is actually going to be the symmetry matrix? Okay, now I would like to achieve something which is A prime equal to SA. And that this S actually shift the mass by a distance of A, right? So what would be the functional form of this S matrix? It will look like this. It's going to be 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0. Looks like this. Okay? So the next two diagonal term is all 1. All the rest of the component is 0. Okay? And this looks a lot more friendly compared to n minus 1k matrix, right? Still, this is a horrible thing to do because this is an infinite number times infinite number dimension matrix. Okay. So we would like to find the eigenvectors of S matrix. Okay? So this means that if I manage to solve the eigenvalue problem, assuming that, okay, I haven't solved it, but assuming that I can solve it, okay, then what I'm going to do is going to get is SA will be equal to beta A, where A is actually an eigenvector of S matrix. Okay? And the SA, we just learned from here, right? It's actually equal to A prime. So beta is the eigenvalue, and the A is actually the eigenvector. So that means originally I have A, which is something A, J plus 1, J plus 2, blah, blah, blah. Okay? And the A prime, after I actually multiply A by S matrix, I get A prime, which will look like this. AJ plus 1, AJ plus 2, AJ plus 3. Okay? So what I'm going to do is, what actually this S matrix does is to shift the A component by one row, right? Okay? So then we basically get this expression, okay? And of course, A1 is equal to beta, which is a constant times A, right? So if you compare, for example, here, okay, you can get that AJ prime will be equal to beta AJ, which is actually equal to AJ plus 1, right? AJ prime is actually equal to AJ plus 1, right? It's just shifting one unit in the label, right? Okay? So this is actually the expression I'm looking for. Okay? We don't know yet what is actually beta. Okay? Beta is some number, assuming that I can solve the eigenvalue problem. Okay? But I do know if I have A0, if A0 is equal to 0, okay, from this expression, okay, that means A1 will be A0 is equal to 1. Or if A0 is 0, then everything is 0, right? And it's not found, right? Okay, A0 is equal to 1, then something will happen. A1 will be equal to beta, right, from this expression, right? Because beta AJ is equal to AJ plus 1. A2 will be equal to beta squared, etc., etc. And then I can say that AJ, if I assume A0, if A0 is equal to 1, then AJ will be equal to beta to the j. Okay? Am I going too fast here? Everybody is following? No question? No? Good. Actually, we found that we have already solved the eigenvalue problem, right? Because I have already the expression for the AJ, which is actually in the form of beta to the j, right? So beta is some kind of number, okay? And the infinite number of beta actually can satisfy this eigenvalue problem. No matter what kind of beta I choose, it can be 1, it can be 2, 3.14, it can be pi, okay? And what I'm going to get is the corresponding AJ, corresponding A vector, which will satisfy this expression, okay? So that means some magic happened. We have already solved the eigenvalue problem without really deriving a lot of deviation, right? Secondly, another thing which we learned is that there are infinite number of eigenvalue which satisfy this eigenvalue problem. The question is, does that make sense or not? Infinite number of eigenvalues can actually satisfy this infinitely long system. It's kind of making sense, right? Because we have worked on one oscillator, you have one normal mode. Two oscillator, you have two normal mode. Three oscillator, you have three normal mode. Infinite number of oscillator, you should have infinite number of normal modes, right? Okay, so that is actually a very, very good news because we have already solved the problem, and we also know the functional form of eigenvectors. Okay, so let's take a look at those example systems which are actually close to infinity long. So here you have a bell-lab machine which actually can have actually multiple coupled oscillators. Each one of them can oscillate up and down. And you can see that, if I actually try to move them up and down, there are complicated kind of motion can occur from this system. Actually, if I do this, and you see that, there something similar to wave is happening. And if I do this continuously, some kind of like a standing wave is produced, right? And this system is actually really, really hard to describe, right? If you look at how many things this system can actually do, okay? Another example is actually, okay, so you can say, come on, this is actually not infinitely long system, right? You have a finite number, right? So how about I use this system as a demonstration? This is actually a much nicer or much better approximation, okay, to an infinitely long system. You can see that, okay, each mass, I can say, for example, each small component of the spring is actually can be considered as a small m in my graph, right? And actually, now I can actually, instead of oscillating then back and forth, I oscillate then up and upside down. Okay, then you can see that there are interesting kind of motion. I can have this, which is like a standing wave. I can do this. I can stop this system and I can produce a wave, and it goes back and forth. And I can do this like crazy. And then you see that I'm exciting a much higher frequency normal modes, right? And that's really complicated. And the question is, how can we actually understand this kind of system? It seems that this system is so complicated and have infinite amount of possibilities, right? So how are we going to understand this? Very good news is that we have solved the normal mode of this kind of system, right? So the normal mode looks like this, Aj equal to beta j, okay? And the following lecture, the rest of the lecture is to understand what does that mean, and also make predictions, okay? So now we have actually the eigenvectors, okay? That's really nice. So from our previous discussion, if this system actually satisfies the symmetry, have the symmetry described by the S matrix, which I have here, that means n-1k matrix will share the same sets of eigenvectors as the S matrix, right? So what is actually the rest part of the work is to evaluate this n-1k multiplied by A, and that will give you omega squared A. Okay? So I just need to multiply n-1k matrix by A. What is A? A is actually here, right? And what is actually n-1k matrix? n-1k matrix is here, have a kind of complicated structure. Okay? On the other hand, if I only focus on the J's object, okay, the object which is named J, have the label J, okay, then actually I can write down, okay, the right-hand side is actually just omega square A J, right? Because this is actually just, if I only focus on the J component, okay? Left hand side is actually just n minus 1 Ka multiplied by A, right? Okay, so basically there are only 3 terms come into play, right? If this is Aj minus 1, so Aj minus 1 will multiply by minus K over N. Aj will multiply by 2K over N. And Aj plus 1 will multiply by minus K over N, right? The rest of the terms are all 0, okay? It's actually not as complicated as we thought, okay? So if I write it down explicitly, the left-hand side part, then what I'm going to get is minus K over N, capital K over N, Aj minus 1, plus 2 capital K over N, Aj, minus capital K over N, Aj plus 1. Okay? So this is actually the J's term. Okay? Now I can define omega 0 square equal to, it's defined as capital K over N. If I do that, then basically I can see that omega square Aj will be equal to omega 0 square. Okay, I'm taking all the K over N out of the again and write it down as omega 0 square. Okay, minus Aj minus 1 plus 2 Aj minus Aj plus 1. Okay? And also we know from the previous discussion, S matrix and the n-1 K matrix should share the same sets of eigenvectors. Therefore, I can actually try to plug in one of the eigenvector from S matrix, right? Aj equal to beta j. Okay, I can plug that in. Then basically I get omega 0 square minus minus beta j minus 1 plus 2 beta to the j minus beta to the j plus 1. And the left-hand side will be reading like omega square beta to the j. Okay? Questions? Okay. So now I can cancel. I can actually divide everything by beta to the j, right? I can get rid of beta to the j. Then basically I get omega square equal to omega 0 square minus 1 over beta plus 2 minus beta. Okay? And as we discussed before, beta can have any value. Okay? And also you can see from here that, once I know the eigenvalue of S matrix and eigenvector of S matrix, I also know what is actually the corresponding angular frequency of the normal mode, right? By using n-1 K times A, you can figure out what is actually the corresponding omega, the normal mode frequency. Okay? So that is actually pretty nice. But on the other hand, if you step back and just think about what we have been doing, okay? So very good. You have a beta, which is a random value. You can evaluate this thing. Then you can get the corresponding omega. But this something doesn't feel right? For example, if you have beta equal to 2, what is going to happen? If you have beta equal to 2, what does that mean? That means Aj will be equal to 2 to the j. Okay, that's very dangerous. Right? That means, okay, so I deploy the whole system, okay, from the left-hand side of the universe to the right-hand side of the universe, okay? So that means if I go to your right-hand side of the universe, okay, the amplitude explodes, right? It's actually 2 to the infinite number, right? Okay, it's not a doesn't sound like a physical system to me, right? If actually beta is greater than 1, then the right-hand side edge of the universe, the amplitude there will explode. Okay? Doesn't sound right, right? So I don't like that. Okay? Maybe you like it, but I don't like it for the moment. On the other hand, if the beta, okay, again, it's not 1, but smaller than 1, what is going to happen? If the beta is smaller than 1, what is going to happen is that, okay, the right-hand side universe is fine, is finite because the amplitudes become smaller and smaller. But the left-hand side part of the universe, the amplitude still explodes. Right? So what does that mean? This means that if the absolute value of beta is not equal to 1, the amplitude at some point goes to infinity. Okay? So that's actually not very nice. That's because AJ is actually proportional to beta to J. Okay? So in the discussion we have here, we consider beta equal to 1 case. Okay? Otherwise, it's actually things will explode. Okay? So if the absolute value of beta is equal to 1, in general, beta can be exponential I small k a, right? Then actually you can actually get absolute value of 1. Okay? If beta is equal to 1, that means the amplitude of all the oscillators are the same. Okay? All right, so now if we accept this, we only limit ourselves to the discussion of absolute beta value of beta equal to 1. Then beta can be written as exponential IKA. Then if I plug this back into this, basically what you are going to get is omega squared is equal to omega 0 squared 2 minus exponential IKA plus exponential minus IKA. Right? Because you have minus 1 over beta, the beta, therefore you have exponential IKA and the exponential minus IKA. Okay, it's a lot of math in this this lecture, but we are getting over to it. Okay? All right. So that is actually, we actually can identify this, and this actually can be rewritten as 2 omega 0 squared 1 minus cosine Ka. Okay? We have arrived a surprisingly simple expression. So let's take a look at this expression carefully. So that means for each given k, a small k, okay, then I will have a corresponding angular frequency omega squared. Okay? So still there are infinite number of possible normal modes, okay, from this. So if I take a look at the amplitude, okay, so if I select a k value, okay, small k value, if k is given, I can actually calculate the corresponding AJ. So the AJ I can actually define as a superposition of exponential ij Ka and the minus exponential ij Ka. And that will give you a sinusoidal shape. So if I give you the k, okay, basically you will see that if I give you the k, then you get the corresponding beta, right? And you are going to get omega, the corresponding omega square. But one interesting thing of this expression is that if you give beta or give 1 over beta, you are going to get the same omega. Therefore, I can now use superposition principle. Basically, I can actually add these two solutions together since they are going to be oscillating at the same frequency. Then what I'm going to get is that, interesting thing happened. The AJ, the amplitude as a function of J, is like a sinusoidal function. Okay? So that is actually what is actually really predicted to an infinitely long system. For example, if I do this, you can see that, indeed, I can see sinusoidal shape. Okay? And you can see that this sinusoidal shape is actually oscillating up and down like a standing wave. And that is actually exactly this expression. So that tells you something really interesting. That means this sinusoidal shape is associated with what? Associated with translation symmetry. Right? All I have been doing is to require there's a translation symmetry. Then you already get the amplitude AJ. And if you choose the physical beta value, then you already immediately arrive a solution which is actually like sinusoidal shape. Isn't that sounds really amazing to you? Okay, so I think it's time to go to take a 5-minute break because I can see that you are overwhelmed by the math already. And of course, let's come back in 5 minutes, then we can discuss some more about what we have learned from this mathematics. And if you have any questions, please let me know. Yeah. Okay, so welcome back, everybody. Of course, you are welcome to come back here and play with the demonstration. Okay, so very good. So during the break, there are several questions asked, which I think those are very good questions, and that's actually the purpose of this break. So it's a long day already, right? A lot of mathematics, and I hope everybody survived. Okay, no dead body yet. Okay, you can see that here I'm doing something really crazy here. So, okay, consider, okay, I think most of you got this point. Beta not equal to 1 is not nice. Something explodes at the edge of the universe. So I don't like that. Therefore, I consider only the case which you have absolute value beta equal to 1. And then we say, okay, it can be plus 1 and minus 1, but that's actually not the whole story, right? You can have, in general, beta equal to exponential I some number, right? Some real number, okay? And I write here a very fancy expression, beta equal to exponential IKA. Why IKA? It's a very good question, right? What is A? I think most of you actually already forgot. What is A? A is actually the natural length of the spring, okay? So I was going to fast because I would like to get to a break to hear your questions. So what is A? A is the natural length, okay? And the K, what is K? Later you will figure that out. You'll find that actually K is a wave number, okay? So that is actually much more meaningful now, right? After the explanation. So you can see that beta is equal to exponential I some number, and I call it Ka, a fancy name of this number, and it has some physical meaning, okay? Another thing which is interesting is that if I plug in beta equal to A or beta equal to 1 over A, okay, into the same expression, okay, if I plug in either beta A or beta equal to 1 more over A to this expression, I'm going to get exactly the same omega. So that means, okay, both value will be oscillating at the same frequency. Okay? So if you choose beta equal to A, choose beta equal to 1 minus A, they are oscillating at the same frequency. What does that mean? That means linear combination of eigenvector coming from beta equal to A and eigenvector coming from beta equal to 1 over A, linear combination of those eigenvectors are also eigenvectors of the n-1k matrix. Okay? And that's actually where, okay, those are different eigenvectors for S. But the linear combination of these vectors are all the eigenvector of n-1k matrix and with the same eigenvalue omega squared. Okay, so that's another thing which is important. And finally, I said that there are infinite number of choice of k. That's valid, right? Because you can choose arbitrary number, then you get a corresponding beta, then you get a corresponding omega. So you have infinite number of normal modes. Secondly, if I give you a k, okay, if I give you a k, or I can give you another value which is minus k, okay, then that means you will get beta and 1 over beta, right? Minus k will give you 1 over beta, right? And as I mentioned before, beta equal to A and beta equal to 1 over A will give you the same omega. Therefore, a linear combination of the vectors are also eigenvector of n-1k matrix. So that's actually what I'm doing here, right? So in order to show you a real amplitude, I'm doing a linear combination of exponential ijka and the exponential minus ijka. It's just a choice, okay? Of course, you can say, okay, I choose plus and divide it by 2, then you get the cosine, right? But if I choose this expression, then what I'm going to get is that, since both of them both vectors are corresponding to the same eigenvalue omega squared, therefore, linear combination of them also oscillate at the angular frequency of omega. Therefore, if I calculate this and make it real, then I found that the amplitude as a function of j is actually a sinusoidal function, which is sine jka. Okay, so what does that mean? This means that if I plot the A, if I plot aj as a function of j, this is actually what I'm going to get. It's a sinusoidal shape, okay? And we know that xj is actually equal to aj cosine omega t plus phi, right? Omega, I can actually evaluate that, right, from here, right? Just a reminder. And what we are going to get is when this system is in a normal mode, okay? Actually, this system is still a discrete system. So I actually would like to point out that as a function of j, only discrete location have mass, right? So you see that those are individual mass. They are oscillating up and down. Okay? And you can see that, okay, since they are oscillating up and down, therefore, the oscillation is actually going up and down. Therefore, what is actually the normal mode of this infinitely long system? The normal mode are actually standing waves, but they actually only appear in the discrete value of j. And it has a functional form of something like a sinusoidal shape or cosine. Okay, so that's actually what we learned, and actually you can see that from here. So if I oscillate this at some selected amplitude, okay, not quite get it. Yeah, so you see that, okay, it's roughly like a standing wave with a fixed frequency. Okay, I would like to discuss with you a really interesting selection. So if I now take a look at, so we have went through a lot of math, right? So now is the time to enjoy what we have learned, right? So if I now take an extreme value, cosine Ka, okay, equal to -1, okay, then I am reaching the maxima oscillation frequency, right? So if I choose cosine K, small Ka equal to -1, okay, what is going to happen is like this. This is as a function of J. If I plot the Aj as a function of J, what you are going to get is something like this. Those are actually the amplitude of individual mass. So you can see that if cosine Ka is equal to -1, omega squared, based on that expression, 1 minus -1, you get 2. Therefore, you get omega squared equal to 4 omega 0 squared. Okay? And if you plot the Aj as a function of J, that is actually what you are going to get. You actually have maxima stretch to the system, right? You can see that it's actually positive, negative, positive, negative, positive, negative. That will reach the maxima speed of the oscillation. And of course, we cannot demo infinite number of oscillator, but of course I can demo a system with 10 oscillators. So you can see that now I maximize the amplitude of the highest frequency normal mode, and then I let go, and you see that this is actually exactly what is going to happen when I have cosine Ka equal to -1. Then the wavelength is very small, and you actually reach the maxima speed. Maxima speed is actually to be compared with, for example, a lower frequency modes like this one, right? This is actually oscillating at a much lower frequency. And you can ask, okay, does that make sense if I have this really, really zigzag shape? Why this system should be oscillating at the highest possible frequency? Why is that? It also makes sense, right? If you have that set up, then you are stretching this system to the maxima possible amount, right? So actually now the springs looks like this. You are stretching it really hard, and therefore the restoring force is going to be large. Therefore, you get high frequency. Okay? Okay, so I hope you actually enjoy the lecture today. It's a lot of mathematics, but what we have learned is really a lot. We learned how to actually describe a system, how to actually solve a system without actually touching the n-1k matrix. We can actually already get the eigenvectors. And using the n-1k matrix, we can actually evaluate omega as a function of the input parameter from S eigenvalue. And the next lectures, we are going to discuss more examples and make the whole system continuous. Thank you very much. And if you have any more questions, I'll be here. I'm very happy to answer your questions.